Yes. Good morning to everyone. I welcome you all to the 40th lecture in the lecture series in Nonlinear Dynamics conducted by Department of Nonlinear Dynamics, Bharathidasan University with the support from RUSA 2.0. It is my pleasure to welcome and introduce today's speaker, Professor Akhmediev from Australian National University, Australia. Professor Akhmediev is a well-known person in optics community and integrable systems group. Since more than half of the participants are postgraduate students, I would like to read out his biodata in a very brief manner. Professor Akhmediev is working on nonlinear dynamics and optics for the past 4 decades. He has published more than 450 papers, including conference proceedings, book chapters, and review articles. He has also written few books on solitons. He works on several topics in nonlinear optics, including optical memory, nonlinear surface waves, bifurcations of solitons, modulational instability, and exact solutions of nonlinear Schrodinger equation, to name a few. Professor Akhmediev has a wide international scientific collaboration. I have not met him so far, and today I feel very fortunate to hear his lecture, at least virtually. With this short introduction, now I invite Professor Akhmediev to deliver his lecture. Over to you, sir.
Thank you very much for a nice introduction. Thank you very much for invitation to give a lecture. It's my pleasure to give it to Indian audience. I've been in India only once in 1997, and it was a long time ago. So it's nice to be in India again, although through online modern technical means. So my today's lecture will be not on integrable systems, but on dissipative systems. Sometimes dissipative systems also can be integrable, of course, but generally speaking, they are not. There is a loss and gain in these systems, and energy comes into the subsystem and goes out. So it is not isolated system. It's the system which is connected to the external world. So to be more specific, let me put the slides. Can you see the slides now?
Yes, yes, sir. Yes.
Okay. So we can distinguish between integrable systems. The known cases are nonlinear Schrodinger equation and Gordon equation, for example. These systems are they can be they have infinite number of degrees of freedom, infinite number of conserved quantities, and they can be solved exactly for given initial conditions. So they're mathematically quite advanced, the most advanced systems so far. On the other hand, integrable systems, they are only subset of more general Hamiltonian systems, which conserve only a limited number of conserved quantities, but not infinite number required for integrable systems like nonlinear Schrodinger equation. Nevertheless, Hamiltonian systems, they are also useful, and they cover more types of systems that exist in nature. And Hamiltonian systems are subsystems of more general dissipative systems. In the latter case, we take into account dissipation, take into account energy coming into the system, And when these are included into consideration, then we are dealing with dissipative systems. So we should not confuse dissipation only with losses of energy. If the energy is coming to the system, it's also a dissipative system. That is a definition. Let me give you a few examples, very simple examples. This is a system with 1 degree of freedom, which is a simple pendulum. And on the left-hand panel of this slide, you can see an ordinary mathematical pendulum, which is mass on a string. And it has one parameter, angle, phi of deviation of the pendulum from the vertical. And it's described by this simple equation when the amplitude is small. It's linear equation. It has a parameter frequency, and this is the frequency of oscillations. So this is an example of this is a completely integrable system. Of course, all solutions can be written in analytic form, but it is the simplest system. It has only 1 degree of freedom. When the angle of deviation from the vertical line becomes bigger, then equation also is different. We have to add sinus function in here. And then the system becomes non-linear. Non-linear means that frequency now depends on the angle, on the maximum amplitude of oscillations. Although solutions can be written in analytic form, but these solutions are nonlinear, not like in the previous case. And finally, if we put a pendulum into a liquid, then inside of the liquid there are forces which prevent free motion of the pendulum, and the system becomes dissipative. So this dissipative term is included into equation, and if there is only this dissipative term, of course, the oscillations will decay. The amplitude will decrease in time, and oscillations will stop exponentially. In order to keep oscillations alive, we need external force. So if this external force F is also oscillatory, then it can keep oscillations alive with certain with fixed amplitude at the end. And this is an example, simplest example of a dissipative system. More complicated example of a dissipative system is van der Pol oscillator. And the equation for this oscillator is shown on the top of this slide. We can see that dissipative term, which is linearly depend on velocity, it also depends, dissipation depends on the amplitude. And when the amplitude is small, it is actually dissipation becomes gain rather than dissipation. And the oscillations in this case becomes increase the amplitude in time. On the other hand, when the amplitudes become too large, then it turns into dissipation, and then amplitude will decrease in time. So this is an example. It's also with 1 degree of freedom, but nevertheless, this is a more complex system than previous one. it has one parameter mu, and if mu is small, then on the phase plane we have circled trajectory, and oscillations will, in this case, will be harmonic. But as soon as mu becomes larger, then of course there's nonlinear oscillations. They are not just described by sinusoidal function, they are more complicated. We can calculate the oscillations using numerical simulations. And on the phase plane, this is called phase portrait, where we plot amplitude versus velocity. Then there is this red trajectory is a limit cycle, so-called. If we start, if the initial condition is located on the limit cycle, oscillations will last forever along this red line. On the other hand, if initial conditions is somewhere outside, then the trajectory moves towards the limit cycle and finishes at limit cycle at infinity. On the other hand, if the initial condition is located inside of the limit cycle, then amplitude of oscillations increasing, and again we are end up on this limit cycle, and this limit cycle for finite mu is, in this particular case, mu is 1.5. Then it's not a circle, it's a complicated limit cycle. And if we just plot the amplitude versus time, we will see this complicated curve, which is known as relaxation oscillations. This type of devices which produce this type of curve used, for example, as blinkers in if they are implemented electronically, use as blinkers in the cars. And this is example of a practical application of relaxation oscillations. So this is an example, another example of dissipative system. Again, it's simple one. It has only 1 degree of freedom. Nevertheless, it has complex behavior, which I described using this phase portrait. Now, if we move to systems with more degrees of freedom, so I will move directly to infinite number of degrees of freedom rather than just one. Then, if we will be talking about nonlinear Schrödinger equation, as we know, it has Soliton solutions, and Soliton solutions they have a free parameter, amplitude of the soliton, and amplitude of the soliton is directly related to the width of the soliton, and so soliton solutions are can be considered as one parameter family of solutions. So this can be plotted as a curve on a phase portrait or any other phase space which you would like to make for soliton solutions. And solitons, they are known as solutions which keep balance between nonlinearity and diffraction or dispersion, depending on are we talking about spatial problems or problems in time. So each soliton solution is a result of the of such balance. But because parameter can be changed, amplitude of the soliton can be changed, then this balance, of course, is different at any point of this curve. But nevertheless, we have infinite number of soliton solutions, and each of them has this property to be a balance between the two physical phenomena. The same happens in Hamiltonian systems, not necessarily for a nonlinear Schrödinger equation. If we extend nonlinear Schrödinger equation, adding other nonlinear terms, then this equation also has solitons. So it's a more general one. We can talk about Hamiltonian systems, and in Hamiltonian system, again, there is a family of soliton solutions which have basically the same properties as for nonlinear Schrödinger equation. On the other hand, if we add dissipation and gain, we have to add them simultaneously, because if it's only dissipation, soliton will decrease its amplitude in propagation. And at the end, the amplitude of the soliton will exponentially go to 0, and soliton will die. In order to keep soliton alive, we should add a gain into the system, and then there has to be a balance between loss and gain. So instead of a family of soliton solutions, we will have a fixed soliton solution, which is a result of a balance between dispersion nonlinearity and between loss and gain. So this solution will be a more complicated balance than just in Hamiltonian systems. And this complicated balance has to be studied in detail in order to understand it. This is just simple physical principles, but this simple physical principle doesn't help us to find the shape of the soliton and other parameters. So in order to find those parameters, we actually need to solve the equation. So in principle, this is the general idea of dissipative soliton as I described, and it comes of clearly classical soliton theory. And then it comes from the ideas of nonlinear dynamics and theory of bifurcations. And it comes from the Prigozhin's ideas of self-organization, because every soliton solution in dissipative system can be considered a self-organized system. So the whole idea, principles of dissipative solitons, they can be understood if we use all of this knowledge in analyzing dissipative solitons. Now let's turn into the actual equation. If we look into this equation, we can see on the left-hand side, it's a classical nonlinear Schrödinger equation. If you recognize it, the first term, it's first derivative. In mathematics, it would be time derivative. If we are talking about optical fibers, this Z is distance of propagation along the optical fiber. The second term is responsible for dispersion in optical fiber, and D is the parameter of dispersion. Dispersion means that various frequencies, because soliton has several frequencies, each frequency propagates with its own growth velocity, and at small amplitude, of course, when the system is linear, then any pulse would increase its width, and then soliton or pulse will disappear. So soliton can appear only if we add this nonlinear term in this case, cubic nonlinear term. And then the balance between dispersion and nonlinearity allows for this equation to have Soliton solutions. And Soliton solutions, they have fixed shape in propagation, and the width stay constant, the amplitude stays constant, and this is the property of Hamiltonian system which admits Soliton solutions. So next a term on the right hand side is a linear gain term. It's just a simple term, the same would be as we would add for simple pendulum. And if only this term is added, then Soliton, of course, will decrease its amplitude on propagation and disappear at infinity. In order to prevent this dissipation, we have to add nonlinear gain and loss term. So next term, which is cubic, has to be positive. Epsilon has to be positive in order to compensate ordinary dissipation. It's cubic, the same as on the left-hand side. This is the lowest order term which we can add for optical fiber. So this term keeps Soliton alive, provided that epsilon is positive. Next term is a quintic term, which is necessary in laser systems, in fiber lasers in particular, and the coefficient mu, quintic nonlinearity, has to be negative in order to prevent the infinite increase of the amplitude of the soliton. This may happen with just the cubic term. It's not sufficient. So quintic term keeps increase of the amplitude at fixed level. This can be considered as nonlinear saturation term. Then if we are talking about lasers, we have to add a spectral filtering term, which is second order derivative, the same as dispersion, but yeah, it's imaginary, as you can see, so it belongs to the dissipative term. And this term allows to pass central frequencies in the laser and with maximum amplification. And at the tails, amplification decreases, and so it introduces this filtering of the of any signal that passes through the system. And finally, we can add higher order nonlinearity, which is not a dissipative term, so it in reality it should be on the left-hand side. And this term makes integrable nonlinear Schrödinger equation. It makes it Hamiltonian. Still, energy is conserved if we add only this term, but generally, system remains Hamiltonian.
Professor Akhmediev, I have a question.
Yes.
Actually, why this minus sign for this quintic term?
Minus term is for convenience, because nu in here could be positive or negative, but convenience is that that if we take this term to the left-hand side, it will be positive.
Because other terms are plus signs only. This.
Yeah, it could be both positive and negative. It depends on the physical system, and in lasers, yes, indeed, depending on the materials used inside the cavity, it can be both positive and negative.
Okay, thank you.
So now let me give you these simple explanations in terms of known systems. If we are talking about laser systems, and we are talking about pulse, roughly speaking, Gaussian pulse, bell-shaped pulse is general. It's not necessarily Sheck pulse as for soliton in nonlinear Schrödinger equation case is generally bell-shaped pulse. And because in the equation which I described in the previous slide, there are derivatives involved, so loss and gain will the dissipative part on the right hand side could be positive or negative depending on the shape, on the profile of the curve. So in this particular case, on the tails, it could be a loss. In the middle, it also could be loss, and gain could be somewhere on the tails. All depends on parameters used in the Ginzburg-Landau equation. And if this is the case, we can see that amplitude in these parts would tend to increase, but then energy will be redistributed to the tails and to the center. And the same happens on the left-hand side and on the right-hand side of the soliton. And as a result, we have a balance between gain and loss. And then the shape of the pulse remains constant in propagation. And again, there is a balance between nonlinearity and dispersion. Of course, that balance also tries to keep the shape of the soliton in certain range. And this complex balance between gain and loss and dispersion and nonlinearity will tend to bring the soliton into certain shape. And this certain shape can be very complicated, and I will discuss this on slides afterwards. Let me give you, before moving to those slides, another example. This is our sun, which shines, it emits energy, shown by red arrows, as we can see. So this energy is generated inside of the sun due to various processes, thermonuclear reaction, and energy generated should be equal to energy radiated, and this is the balance between the two energies. On the other hand, there is internal pressure which develops inside of the sun due to all these reactions, and gravity which acts in the opposite direction. So we have another balance between internal pressure and gravity. And then total balance is very complicated, and this total balance keeps the shape of the sun is fixed, at least for a certain amount of time. And due to this stability, we can, on Earth, we can receive energy and live for a while as well. Luckily, this is billions of years, so we shouldn't worry about what will happen in future too much. But this is another example of a dissipative system with complicated balances, which keeps the system fixed in time. Now let's turn to Ginzburg-Landau equation, which I discussed above, and a certain shape of solitons, which this equation admits. And these shapes, they are for a certain set of parameters. So set of parameters have to be fixed. When we fix them, And if we start numerical simulations with some shape, initial shape, this shape is not a solution. We just guess closest to what we can get as a result of simulations. And this initial condition, it converges to the shape, which is fixed. And at the end, we have this complicated Soliton shape, as we can see. It's not just bell shape. It has 3 peaks in this particular, in this particular case. So that solitons in Ginzburg-Landau equation can be very complicated. Of course, there are simple shapes, bell-type shapes for Ginzburg-Landau equation, but this example is a bit more complicated. Another type of the dissipative soliton is pulsating soliton. This soliton changes its shape in propagation. It changes its shape periodically, and after one period, it returns exactly to the same shape as at the beginning of this simulation. And after the second period, again, it returns to the same shape. And this solution is, again, although it's not fixed, but nevertheless, if we start with any initial condition, like in the previous case, it will converge to this pulsating solution as shown on this plot. And in this sense, the solution is fixed for given set of parameters. This periodic solution is the same no matter what kind of initial condition we used at the beginning of simulation. So this is another type of solution which we would call pulsating solutions. And there are infinite number of these solutions. We can slightly change parameters and still get a pulsating solution. It will have a different shape, different period, but nevertheless, it will be the same type pulsating solution of Ginzburg-Landau equation. Then another type of solution, it's also pulsating, but pulsating not periodically. It pulsates chaotically, let's put it this way. If we plot the energy, for example, energy along horizontal axis and the maximal amplitude, maximal intensity along vertical axis, then we would have a trajectory in this plot, in this phase space. It will be oscillating motion, but this oscillating motion will not be exactly periodic. So each time when we have next oscillation, the point is shifted, and these shifts never repeat, never turn back to the same trajectory. In this sense, this solution is chaotic, and so it's another type of the solution which nonlinear Ginzburg-Landau equation may have when we change the parameters. Parameters are shown here. Another type of solution, we can call it exploding solitons. Again, we can have this type of soliton starting from any initial condition. At the end, it converges to a certain shape, but this shape of the soliton actually is not stable. It's fixed, but not stable. So instability brings the solution into this explosion. So soliton explodes into many pieces, and when explosion ends, all parts they dissipate, and at the end we have exactly the same shape as at the beginning in here. And explosion happens intermittently, so not exactly periodically, but with certain average period in time. It's another interesting type of solution which nonlinear Ginzburg-Landau equation may have. And we can see that there could be infinite number of different type of solutions, because we have 5 or 6 parameters in the equation. This is 5 parameter space, 6 parameter space if you want. And of course, to investigate all these enormous space is nearly impossible. So we can only provide certain examples for a given set of parameters, which and then find interesting examples of solutions which the equation does admit. Here is another, yes?
There is a question from one of the participants.
Yeah.
He's asking pulsating in the sense not continuous solution. He's asking something. Is it because the system is not integrable, or it is intrinsic property of the pulse?
No, this is if it's integrable system, as I explained, there are only one type of solution, like for nonlinear Schrödinger equation. It's only Scheck type of a Solitons solution, a finite one, I mean. But in Ginzburg-Landau equation, there could be infinite number of types of solutions. And this is an interesting property of a dissipative system, which doesn't exist in the case of even Hamiltonian system.
Okay.
Mm-hmm. So this is another interesting Soliton solution, which has 5 maxima, as you can see. You can get it if you take parameters shown in this panel. Again, you can start with any initial condition, and this initial condition will converge exactly to the shape which is which appears for this set of parameters. And the energy, if you calculate the energy across the soliton, in this case, is shown here in green letters. So this is these are 2 examples of pulsating solitons. This is simple pulsations on the left-hand side, and on the right-hand side, these are more complicated pulsations, and the difference between them is the set of parameters which are used for simulations. When we are dealing with pulsating solitons, we can plot any 2 parameters of the soliton, energy, for example, along horizontal axis, and the maximal amplitude. And if we have exactly pulsating solution, then this will be a limit cycle. Of course, we can start at any point of this phase space, but gradually it will converge to this limit cycle. And for pulsating solution, we will have this limit cycle at the end of the evolution. And this would be a proof that we are dealing with pulsating solitons. Then if we slightly change parameters, for example, then a simple limit cycle can split into 2 limit cycles, which are transferring into each other. So this is a phenomenon which is called period doubling. Instead of a single period, we have period 2 in this case. And after 2 periods, we return exactly to the same trajectory as before. And then we have a limit cycle, but more complicated than in previous case. This limit cycle in turn can be splitted into 4, and this way we have so-called period quadrupling, but for such complicated system, which is infinite dimensional, infinite number of degrees of freedom. So it is not the same effect as for simple systems, simple maps, but it is highly complicated phenomenon for Ginzburg-Landau equation. In general, we have 6 parameters, but if we fix 4 of them, for example, and plot 2 of them in a 2-dimensional space, for example, beta, which is spectral filtering, and cubic gain or loss, then depending on these 2 parameters, we have various outcomes of our numerical simulations. We can have fronts. Fronts would mean that on the one side of the solution it will be 0, on the other side it will be fixed amplitude, and we can have a front between the finite amplitude and 0. Below, in this right bottom side part of this plot, we have plane pulses, just ordinary solitons which do not make change shape. Then in the middle we have in here pulsations, ordinary pulsations, and these pulsations can be turned into chaotic solutions or into fronts. In this particular case, this right-hand side front can move to the right, left-hand side front can move to the left, and then soliton is transformed into a simple front. And the same we can do plotting cubic gain, for example, and quintic nonlinearity. In this case, it is negative, and make a plot. Of course, each plot of this type requires enormous number of numerical simulations. So we start at a certain point and wait until, start with some initial condition, wait until it converges to certain certain solution, and only then we can conclude that indeed we have a stationary solution of Ginzburg-Landau equation, and then we can put a point on this plot. So this is a chaotic solution of the type which I discussed above. And in order to confirm numerically the existence of these solutions, we can use fiber lasers, which consist of part of the cavity, which is the fiber with doped fiber, which has atoms, ions inside, which emits light when it's pumped externally. So in this part of the pump, in this part of the fiber, the energy of light increases. Then we should have nonlinear transmission element, which is called mod locker. It can be different designs. And as a result, we have all nonlinearities which are in Ginzburg-Landau equation. And in order to observe those pulses, we should have a coupler or splitter. As part of the energy at the splitter will go out, and then we can measure parameters of the pulse outside of the cavity. So this cavity can generate pulses which can be observed in numerical simulations. And many of those pulses, they have been confirmed. Indeed, those solutions, they do exist. Generally, of course, the design which I presented above is not continuous. It has dispersive part, ordinary optical fiber. It has gain part, the part of the fiber which has which is doped by atoms emitting light, ions. And then, of course, numerical simulations could be more complicated. It's not a continuous system. It's Ginzburg-Landau equation with parameter management, as we can see in this diagram. But in this system, again, there could be limit cycles as shown in this plot, and those limit cycles can be observed experimentally. So this plot shows generation of stable pulses in a cavity. Every round trip we can have a pulse, and all these pulses are the same. It's a stable regime of pulse generation in a laser cavity. So perhaps we wouldn't have more time for more complicated topics in this talk. Maybe I should stop and answer the questions on the previous part.
Yes. Ramakrishnan? Yeah, Prof. Name, there is one for Mr.
Yes.
Ramakrishnan. You want to ask some question? Ramakrishnan, are you there?
Yes, sir. Yes, sir.
Yeah. May I ask now?
Thank you, sir. Thank you for your nice talk.
Yeah.
I have very basic questions, few basic questions. So my first question is, shall we claim these dissipative solitons as strictly solitons? Because in textbooks, usually we read solitons are the solutions, integrable, infinite dimensional systems.
Yes, ordinary solitons, they of course solutions of integrable systems, but this term has been extended later to Hamiltonian systems, which are not integrable. Still, in the papers, people call them solitons, although we should of course explain that they are not integrable solitons, but Hamiltonian solitons. And in case when we are dealing with the Ginzburg-Landau equation, these are dissipative solitons, as I explained at the beginning. So this additional word dissipative, it explains that these are not those solitons which mathematicians they used to call solitons. These are different objects.
Okay. Okay.
Mm.
So pulsating solitons and breathers are different, sir.
No, they could be called breeders, of course, but breeders, again, there are a variety of breeders. Breeder solutions, they could be periodic solutions in transverse direction. There could be breeders which do it only once. And so the notion of breeders is much wider than just pulsating solitons. Pulsating soliton is a localized solution, localized object, which evolves periodically. And breeders are has a much wider definition.
Okay. Okay. So if that is the case, is it possible to construct rational solutions in these dissipative systems?
Generally, there are no exact solutions for those dissipative solitons which I demonstrated. They can be obtained only numerically. And although exact solutions, we can write some exact solutions for Ginzburg-Landau equation, but those soliton solutions but those soliton solutions are not stable. And if we try to start, use them as initial condition, they will not be stable. So those exact solutions are not solitons which we can observe in reality.
Okay, sir. Okay. Okay, sir. Thank you.
Any other questions?
Mhm.
Hello, sir.
From students?
Sir, I'm audible, sir.
Yeah, Prasad, yeah, go ahead.
Yes, sir. Yes, sir. Actually, that pulsating soliton, like you said, that pulsation of the soliton creates a limit cycle. So, what is that, sir? So,
What is limit cycle, you mean?
yes, sir. That the pulsating of the soliton it correspond to the limit cycle of the soliton. So, I couldn't.
The limit cycle, the notion of limit cycle comes from nonlinear dynamics, from starting from systems with 1 degree of freedom. One example of limit cycle I showed you, it is relaxation oscillation. All those dynamics can be represented on two-dimensional phase space. And in two-dimensional phase space, it is just a closed curve. And that closed curve can be extended. That notion can be extended to systems with higher number of degrees of freedom, 2, 3, and more. And then phase space becomes also more complicated. You cannot represent it in two-dimensional plane. You have to use more complex phase space. And in our case, it's infinite dimensional phase space. But of course, normally we cannot deal with infinite dimensional phase spaces. And we can use only two parameters of the solution and make this simplification. And then in this two-dimensional phase space, representing only two parameters of the solution, we can have also the same kind of curve, a closed curve, which we can call limit cycle. And indeed, it will be a limit cycle, physically speaking.
Okay, sir. And the period doubling of that limit cycle is correspond to the bound state of soliton or what, sir?
No, period doubling happens when it is so-called bifurcation. Again, this notion comes from nonlinear dynamics. If we change parameters, for simplicity, we can keep 5 parameters fixed and change only 1 parameter. And at certain point, at certain boundary, limit cycle will split into two curve. Instead of one simple limit cycle, it will be doubled limit cycle. Then this point will be called bifurcation. And because we have period doubling instead of a single period, we have two periods as a single period, and bifurcation to this from simple limit cycle to period doubling would be period doubling bifurcation.
Yes, sir, because in that plot, amplitude, time, and space plot, it was shown that because of period doubling, it was formation of two pulses. So I was thinking that is it a signature of bound state of two soliton or what, sir? That period doubling, is it correspond to that or it's different? What I'm thinking.
Correspond to no, soliton is always bounded. Its It is a solution which zero at infinity.
No, so soliton molecules, like bound state of two solitons.
No, it's not bound state of it's a single soliton.
Okay, so
It's
because
just the behavior of this soliton is periodic. And
okay,
it's not simply periodic, it has more complicated than that.
okay, sir. Okay, sir.
So it's not bound state of two solitons. Although there are solutions in the form of bound state of two solitons as well, but those are much more complicated.
So can these solitons, dissipative soliton, can propagate in optical fibers? Is it possible? Can we think
Well, yes, all these fiber lasers, these are dissipative solitons propagating in an optical fiber.
Yes.
And those fiber lasers are the simplest devices where we can observe them because there would be correspondence between the design of the fiber and parameters of Ginzburg-Landau equation. And then having this correspondence, we can observe objects we observe numerically in real experiment.
Yes, because in the laser cavity it was observed. So because in a laser cavity it is easy to, like, not easy, but respectively it is easy to like go through those parameters and fix like what you explained later. But in the optical fiber, if you want to give the gain in the way that your whatever the structure is there should be balanced against the loss. So I don't know, like, if there are number of structures and they all wants to be stable while propagating inside the optical fiber, how it would be. That's what I was confused.
Now, of course, you cannot use single mode fiber produced massively by many companies because in a single mode fiber there would be loss, and in certain number of kilometers signal would be lost. So it's not the system which could be used for observing dissipative solitons unless it is a trivial dissipation. So we have to use a little bit more complicated system. We can, of course, add gain along the whole fiber, but again, it's a kilometers of fiber, and then it's again not the system which we want. We want more complicated nonlinearity, and more complicated nonlinearity can be added only using a special transmitting element which could be introduced only in the cavity.
Okay, sir. Okay. And sir, another doubt I had, like, you were giving some like general initial shape, and so that initial shape can be anything, so it won't affect your final solution, like whatever the final real shape will be. So it won't affect. You can give Gaussian shape or sec hyperbolic or tan hyperbolic. So it's not going to affect your final solution, is it, sir? Because
Yes, we can use any initial condition, of course, which must be localized, any shape. But generally, it should be reasonably close to the solution for this set of parameters. Because if it has very small amplitude, then of course it may decay and disappear. If it is too large amplitude, the amplitude can go up, and again there will be a divergence. So there is certain restrictions to the initial condition, but those restrictions are quite large, and in principle, yes, you can say that any initial condition would be good.
okay, sir. Okay, sir. And okay, sir. Actually, the dynamics of these dissipative solitons will be different from the conservative soliton, is it, sir?
Different from what?
The conservative soliton, the NLSC soliton.
Yeah, sure, completely different. These are absolutely different,
Yes.
as explained. Yeah.
Yes, because they used to talk about the pattern formation inside the laser cavity, this dissipative system. So that can't occur in the NLSC soliton, right, sir? Like you can't get bound state of two soliton for the NLSC, is it, sir? For the nonlinear Schrodinger equation.
Uh, No, there is no bound state as such in nonlinear Schrödinger equation because solitons they behave like in linear systems. It's just superposition of solitons. Of course, there could be interference, nonlinear interference between the 2, 3, and more solitons, but in integrable systems, they behave like in linear systems. This is why inverse scattering technique is actually reduction from nonlinear system to linear system. And you cannot observe all that complications of Ginzburg-Landau equation in nonlinear Schrödinger case.
Okay, sir. Okay. I think I should stop here. So there could be some other question. Thank you so much, sir. Thank you, sir.
Ramakrishna, you want to ask something?
Yes, sir. Yes, sir. Sir, is there any common signature of these dissipative solitons during collision? Because in this complex Ginzburg-Landau equation has some additional terms than the normal NLS equation. So means this loss term and gain term. So is there any that collision? Can you comment the collision of these dissipative solitons in Ginzburg-Landau equation?
Yes, there could be collisions, but all those solutions which I showed in the lecture, they actually have zero velocity. So if you consider two solitons, they will be propagating in parallel and they will not collide. In order to have collision, you should find solitons which propagate with certain velocity to the right or to the left. And because of the symmetry, if you have soliton propagating to the left, they will be equivalent solution propagating to the right. And those can be collided. And then the outcome of this kind of collision, it's either a single soliton which propagates with zero velocity, or one of these solitons which propagate to the right or to the left. So because of the dissipation, they in collisions, energy, total energy can be lost, so energy is not conserved.
Okay, so the collisions may not be elastic.
Sure, they are not elastic. They are never elastic. There is no elastic collision as such.
Because of the dissipation.
Okay. Okay. Thank you, sir.
Thank you. Any other questions?
Professor, hello.
Yes.
Professor, people are studying dissipative soliton using Luggiato-Lefebvre equation. So, what is your comment on this?
Well, Luggiato-Lefebvre equation, it's a simpler one. The idea is generally you can use the same ideas as for Ginzburg-Landau equation. But that one is simpler and applicable to certain design of laser cavities. So it's a little bit different, let's put it this way. But generally, the same ideas can be used for Luggiato-Lefebvre equation. Yes.
Okay. Thank you.
Okay, so I have one question. Actually, there is a exciton-polariton condensates. So there we use the dissipative GP equation, Rosberg equation. Is it possible to get this kind of solitons in with that condensate?
This kind of solitons in what?
In exciton-polariton condensates, can we expect?
Mm-hmm.
They are represented by dissipative Gross-Witarski equations, similar to what this analysis equation.
Well, I don't know really, because still you have to have all these nonlinear several
Yes.
terms in the equation. But for exciton polariton case, I don't see exactly how to do it.
Okay.
Yeah.
Okay. Thank you. Is there any other questions? I hope there's none. So it's time to conclude. So I would like to thank Professor Neil Akhmediev for his excellent presentation and spending the time with us. And we really enjoyed this lecture. And thank you very much.
Thank you very much for invitation and for the opportunity to give this talk in your excellent audience. Yeah, thank you very much.
Thank you. Thank you.
Mhm.